Good morning. Really cool to have you all here. Happy Wednesday. I hope you're staying warm. That wind is just brutal out there. Anyway, let's talk about all the things happening this week first. So if you have problem set 5, quiz 5, and the unknown chloride lab, I got some piles going up here. I'd love to get them from you. That would be awesome. We'll continue on with an exam review today and probably Friday. A couple of announcements real fast. Friday, if you saw, if you didn't, it's okay. Friday, I do have another one of these science division meetings, so I'm changing my 10 a.m. office hour to 8 o'clock on Friday. So I won't have 10 a.m. office hour, but I will be there at 8 o'clock. So I'll still be there at noon too, so just FYI. And then Friday, of course, when you come in, we'll take care of the midterm, which is why we're doing all the review, exam prep 2, and we'll do the calorimetry lab. This is kind of a fun lab. If you got your goggles, bring them along. We're going to deal with some strong acids, stuff like that. So I know this is kind of a crazy week. I respect all of you for hanging in there. One more kind of fun announcement. Fun being a strange word. Tomorrow at, I think it's 3:30, excuse me, in 1657, which is one of the math classrooms, they're doing a presentation on infinity and what exactly infinity is. They're going to show this movie, which looks kind of intriguing. They will have free pizza and popcorn. Anyway, there's a little flyer up here. I put something on our Discord Prof Ad Off channel if you're interested. Any questions on anything?
I don't have a question, but I had something to let you know. Sophia texted me a little bit ago.
Okay.
She sent me a picture, but she got what?
Okay.
Tire on the highway.
It's not a problem. These things happen.
So she would try to get here by office hours to try again.
Tell her that's totally fine. Hospital stuff. Exciting week. Other questions? All right. So what we'll do is we'll start talking about the midterm again, stuff like that. We'll go through some questions, and if you have questions on this process, please let me know. All right. So we left off on Monday talking about balanced reactions and the things you can do with them. This is a really important problem, and I want to point out here what kind of problem it is before we get started. So first of all, nitrogen and hydrogen can be combined to make ammonia, and this was actually a reaction that kept Germany in World War I. That's more probably information you needed to know, but it is kind of interesting. But that's not why we're talking about it. What I want you to see in a problem like this is you have two reactant amounts. All right. Now, in this case, they're moles. They might be grams or whatever, milliliters or whatever. But when you have two reactant amounts, you've got to think about a certain concept we talked about. And does anybody remember what that concept is?
Yes.
Which one?
I was gonna say Hess's law.
Oh, cool. Hess's law was used with energy when you want to combine reactions to get an overall one. This is a limiting reactant problem. All right, and so it never says that they're limiting reactant problems, but you can see that if you see that they're telling you there's two reactant amounts, and it's not just an excess, it's an actual amount value. So one of those is going to limit how much ammonia you can make. So see if you can figure out, first of all, what the limiting reactant is, and then finally figure out how much ammonia NH3 should be created. if you look at these two amounts and you know that it's limiting reactant, it might be very tempting to say, well, there's a lot less N2 around, so I'm sure that's going to be the limiting reactant. So if you did that, you'd say, all right, well, there's 1 N2 for every 2 moles of NH3. And again, these ratios come from the balanced reaction. So you'd have 10 times 2, you'd have 20 moles of NH3. So let's say that I do this, I say, hey, Clifford, my boss, we're gonna make 20 moles of NH3, and he goes, cool, that sounds awesome. Should have checked the other one. You can't rely on the initial numbers because you've gotta look at the different stoichiometries. So 25 is obviously a lot bigger number than 10, but to figure out how much ammonia, this process is really important. There is a 3 by the H2 up there. There's still a 2 by the NH3. So 25 times 2/3 is something you should check out, all right? And if it's less than this, then that means that hydrogen's going to be the limiting reactant. On the other hand, if it's more, then that means nitrogen's going to be your limiting reactant. So sure enough, when you try this, you see that there's only going to be 16.7 moles of ammonia made from the hydrogen. So when you compare these two numbers, the smaller number is the golden one, if you will, for chemistry. We will only be able to make 16.7 moles of NH3 because the hydrogen is limiting us, all right? It's the limiting reactant. The N2, even though it's a smaller number initially, because of the stoichiometry, nitrogen is the excess reactant. So if I said to Clifford, my boss, I said, oh yeah, 20 moles of NH3, and he's like, counting up his money or whatever, well, he's going to be mad at me because I should have checked the other reactant to see what's happening. So in chemistry, this is really important, all right? You've got to see how much product you should make. If we had grams of these, you could go grams to moles first and then moles to the moles of the product, something like that. But it's a pretty important process to hang out. But again, the most important thing is that if you see a problem with 2 reactant amounts, that's going to scream limiting reactant, and you've got to check both reactants to see how much product they're going to make. Any questions on that? Now, here's a question. We've got a compound with carbon, hydrogen, and oxygen. And this is a problem where we want to find not only the empirical, but we want to really find the molecular formula of this problem. Now, this is one of those weird ones like we talked about in problem set 4. You've got carbon, hydrogen, and oxygen. And we've got CO2 and water. But oxygen's a little bit of a problem because we don't know where the oxygen is going and coming. So this number right here is going to be important in finding out how much oxygen you have. So see if you can figure out which of these formulas would be the best set of materials for this stuff right here.
Sure.
Yeah.
You have experience with rice mill?
With what?
With rice mill?
Yeah, but let's talk about that later. Yeah, let's stay.
Sorry, I was just wondering if
No, it's all right. It's okay. I like questions like that. Don't get me. Yeah. Okay. This problem is one of the more problems, takes a lot of pieces to put together, but it's all stuff you can do. And up here on the board, I have kind of the general format of what you need to do. It gives you grams of CO2 and grams of water, and you've got to turn them into moles. So you'll divide by the molar mass of CO2 and water to get the moles. Then turn those moles into moles of the elements, carbon and hydrogen. So carbon to carbon dioxide, 1 to 1. Water to hydrogen, you multiply by 2 because of the H2O right there. And those two numbers we'll use here in a little bit. But in this kind of a problem, you want to turn those numbers into grams of carbon and grams of hydrogen. So you multiply by 12, you multiply by about 1, and get those numbers. And the reason for it is that we don't know where the oxygen is coming from. In this kind of problem, oxygen ends up in CO2 and water both, and it came from the organic compound and oxygen. So it's hard to, we can't use like a mole to mole ratio, which you know I'm all over in these kind of problems, but it just doesn't work. So what scientists do is they take the grams of sample, 0.255, and they subtract the hydrogen and carbon from up here. And that gets you to just the grams of oxygen in the sample. All right. And this is kind of the weird part for this kind of a problem. But if you can do that, then that's really awesome. Then you can turn the grams of oxygen into moles by dividing by 16. You can then compare the CHNO to get the empirical formula, and the molar mass of the empirical formula you can compare to 60.1 in order to find the molecular formula. Okay, so here's the math. Oh boy. Anyway, but in a nutshell, this first part here, grams to moles CO2 to moles of carbon, and I put it in red because we're going to use that here in a little bit. And then I took that moles of carbon and turned it into grams of just carbon. Same thing for water, grams to water to moles, multiplied by 2 because of the formula, H2O. That'll get you moles of hydrogen, moles into grams gives you this number. Now this is the part that's important on these. To find the oxygen in your sample, this is the best way I think to do this. Total grams, which is the CHNO, minus the grams of C and H that you calculated up here, that's going to get you the grams of just oxygen. And that's grams of oxygen in the sample. So when you turn that number into moles, you can then compare this moles of hydrogen, this moles of carbon in order to get the empirical formula. And this is the smallest of these, it's 0.00 versus just 0.0s. So you end up with 1 oxygen, 3 carbons, and 8 hydrogens. And if you find the molar mass of this thing, it's also about 60.1. So the EF and the MF are the same thing on this kind of problem. This is super important when it comes to chemistry because in organic chemistry, which dominates most molecules, a lot of them have carbon, hydrogen, and oxygen. So this is one of the things that chemists go through. Any questions on this problem?
I'm just looking at, so in order to get the molecular formula, we get the molar mass of the compound, right?
That's right. That's
Which we just do like some math.
Yeah,
And then divide by molar mass of the empirical formula, which also some math.
that's right.
Okay.
This one you can be kind of rough with, Clifford. Like carbon's about 12, so 12 times 3, 36, plus 8, 36. 44 plus 16 is about 60. Honestly, that's good because this ratio will always be a whole number, no fractions or anything like that. So if you got like 60 and 60.1 was the whole thing, that's 1-to-1 stuff. Yeah, that's a good way to save time. So, good. Other questions? Let's get out of these kind of problems. So anyway, now we're going to move on into how solubility affects things. These are solubility in water. And only one of these is an insoluble salt when placed in water. And see if you can figure out which one of those it is. You can totally use a solubility table if you have it, or looking at the other ions present in the other 4, I think you can figure it out. for the midterm on Friday, you can have a page of notes, all right? And one thing you might want to do is have some version of the solubility in there, all right? However, let's say that you're like, "No, I'm not going to use any notes." Yeah, all right, cool. Then let me give you a couple of hints that will help, all right? Now, these ions up here, all right, I placed up here for a special reason based on solubility. Does anybody know what's quote unquote special about those? They are always AQ. So if you see anything with sodium, anything with acetate, anything with lithium, no exceptions, all right? Those are always AQ in our notes. So looking at these, well, here's nitrate, sodium, all right? Don't have lead or iodide, we'll talk about that in a little bit. But here's potassium and here's lithium, all right? So these four have one of these in there, and they're super common. They show up a lot. So if you see one of those, it's automatically AQ. Now, PB and I2 or iodide are not on there. So the other one, which I find probably pretty helpful for you to know, is that chloride, bromide, and iodide are AQ unless they're with lead, silver, and mercury. So most things with with chloride would be AQ. So nickel 2 chloride, uranium 4 bromide, et cetera, et cetera. But if you have one of these, i.e. lead, then it's going to be insoluble. So most of the time, knowing this little group up here is pretty good for solubility, all right? If you see a hydroxide or a carbonate, I mean, usually those are insoluble, but not with sodium, potassium, lithium, ammonium. So this is kind of like a quick and dirty version of the solubility guide. You may not have to write down all of those notes in your note sheet, unless you want to, of course. But if you know that these guys are always AQ, cool. Questions? All right. Which one of these compounds is not an acid in water? See if you can remember what an acid is all about and which one of those is not an acid.
What does next week look like for homework?
Next week, nothing is due. Next week, we have class on Monday, but there's no labs, nothing's due. The week after is class presentations week, after Thanksgiving and stuff, but that'll get us all fresh.
Basically, their presentations finished on
Yeah. Of course, I'm sure some of you have them ready right now and stuff, but yeah, totally. That week, the Friday of the 10th week, class presentations, and you'll turn in the calorimetry lab, which we'll do today. All right, I'm very pleased. Everybody that voted here saw that it was either going to be A or C, and that's awesome because acids should, in my opinion, always, but they don't, have hydrogen listed first, all right? It's a really important part of the energy of reactions. So chloric acid, hydrochloric acid, phosphoric acid are definitely acids, and you can see that they're listed because their hydrogens are listed first. This little bugger right here is an X compound which doesn't always follow the H listed first rule, and it's not the way I would like it to be, but I'm just the messenger. In organic chemistry, there's a reason why the acetate group, CH2H3O2 or CH3CO2 minus, they're the same thing. There's a reason why that's listed first, and you gotta wait till organic to check that out. But this actually is an acid, all right? The hydrogen is often listed last. And again, I apologize on behalf of chemists, that's kind of unfair. But again, I'm just the messenger. The most common weak base of all is ammonia, and that's NH3. So NH3, which is in all of our cleaners, a lot of things we use at the house to clean up spills and stuff. Ammonia is a base. Ammonia reacts with water to make ammonium, NH4 plus, and hydroxide. It doesn't do a lot of it, but it does do some. So just realize good old NH3 here is a base. Questions on that? All right, here's a reaction that's going to ask you about the action of the reaction, as I called it, aka a net ionic equation. This reaction is for magnesium carbonate reacting with nitric acid. Now, magnesium carbonate is MgCO3, and nitric acid is HNO3. This is an example of a reaction we looked at in the net ionics lab. See if you can figure out what's going on here. Which one is the net ionic reaction? Is anything with nitrate going to be a solid? No. If you picked answer C, you might want to just double check. Okay. So on this problem, magnesium carbonate, MgCO3. Carbonates, usually insoluble. You can probably guess from up there because the MgCO3 is solid, that's what it is. But anyway, HNO3, nitric acid, AQ. The magnesium and the hydrogen trade places, so magnesium starts dancing with nitrate. Magnesium's positive 2, nitrate's negative 1. You'll need 2 nitrates to dance with your magnesium. Hydrogen and carbonate. Carbonate's minus 2, so you'll need 2 positive 1 hydrogens to dance with that. You'll need a 2 right there to make this balanced. So the balanced reaction would be MgCO3 plus 2HNO3, making MgNO3 plus initially what's H2CO3. Any questions on that part? Okay. Now, the states of matter, super important. Let's go back to my quick and dirty list. All right, anything with sodium, potassium, lithium, ammonium, nitrate, and acetate will always be a cube. All right, no solids. All right, so again, it can be blah, 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 nitrate, and you don't know what blah, blah, blah is, and I don't either. All right, no problem. Nitrate, a cube. All right, so I put that down there because several people put answer C, which would be making the solid. And if it was, it would be precipitation, and I totally dig it. However, anything with nitrate, anything with sodium, anything with lithium, a cube. All right. This guy, H2CO3, if you remember from our net ionics lab, breaks up into H2O and CO2. One is a gas, one's a liquid. So what kind of reaction was this from the net ionics lab? Gas forming, that's right, yeah. If you see H2CO3, it's going to be a gas forming reaction because the CO2 and water is made. So, long story short, to pull the spectators out of the reaction, all right, you look for something that has the same species in an aqueous on both sides. And these guys are classic spectator ions, all right? That's another reason why I wanted to kind of point it out here. So nitrate is in aqueous parts on both sides. You don't want to break up the water, you don't want to break up the CO2, and you don't even want to break up the MgCO3 solid, because that's a solid, all right? So this reaction A is the balanced molecular reaction. It shows all reactants and products in all their glory. But we're after the net ionic equation, which is basically this reaction without the spectators. And nitrate is definitely a spectator. It's always a cube. So if you pull the nitrate out of nitric acid and the nitrate out of the magnesium, you get answer B, all right? The nitrate is pulled out. Nitrates are always a cube, all right, just like sodium, lithium, potassium, etc. This is the action of the reaction. As a chemist, all right, you go to the lab and you want to do this, and the stockroom didn't have any nitric acid for you. This is a true story. This happened one time. But anyway, you could substitute in another acid like hydrochloric acid or, I don't know, well, sulfuric acid would be weird, but you could add in different acids and stuff and still have the same results. So. Cool. But the most important things, this little list right here, everything, always a cube, right? No solid's going to be made. Again, it can be, uranium, thorium, any weird combination of elements. And for us in Chem 221, always a cube. Any questions? Let's do another one. This reaction is looking for the net ionic reaction between potassium hydroxide and iron 3 chloride. Now, potassium hydroxide, KOH, iron 2 chloride, and iron 2 chloride, FeCl2. So see if you can figure out what the net ionic reaction is all about. And again, remember this magic little list up here of ions that will always be a cube. And I think that will help in this problem. Another advantage of this little silly list right here is that those ions will never be in your net ionic reaction. So I was just thinking here that looking at this list, all A, B, and D all have potassium, all right? And A, B, and D having potassium means those are not going to be net ionic reactions. They might be something else, but they're not going to be they're going to be spectators, and they wouldn't be in the overall reaction. So it could still be E. It's not, but it could be. So it kind of leads credence to maybe the answer C is right. Now, the best way, of course, to do this, KOH plus FeCl2 are the two compounds. The iron and the potassium trade places because they're both positive. So iron starts dancing with OH minus hydroxide, and potassium and chloride start dancing. Now again, anything with potassium automatically AQ, all right? So FeCl2, it claims here is aqueous, but FeOH2 is the only one we don't know. And most of the negative polyatomic ions, hydroxides and carbonates and sulfates and sulfides, stuff like that, a lot of them are insoluble. And so this would be the only one you wouldn't know maybe from this quick list, but you can maybe make a guess that it is because most hydroxides are. So anyway, this is what you're after. And because in the net ionic you only want solids, then FeOH2 is going to be your product. And the ions that go into that will be reactive, will be the reactants. So in this case, it's definitely answer C. All right. Chlorides are usually AQ. They're AQ unless they're with lead, silver, or mercury, but we don't have any of those in this problem. So chloride is just like potassium. It's going to be AQ on this one. So, you okay?
Yeah, my wrist pop.
Oh, sorry. It's got to be one of those days. Questions on this problem? All right. Here's a question where we've got some zinc reacting with a vanadium compound. Vanadium is named after the Swedish goddess of beauty. Doesn't matter this, but anyway, doesn't matter. The question is, which one of these is oxidized or reduced and or oxidized and reducing agent? So see if you can figure out which of those is the best answer here. I got your message into it. Yeah, no worries. She's got your back. All right, I'm running out of time here, so I have to start talking about this one. Leo, the lion, says Grr. Leo, lose electrons oxidized, Grr, gain electrons reduced. And remember that something that's oxidized is also called the reducing agent. I didn't make those terms, that's what they tell me. Reduced things are also called oxidizing agents. So you have two different terms for the same thing. Again, I'm just the messenger, I hate this rule. But anyway, what I would recommend doing here is, like, you see that zinc is going to zinc plus 2. Now, to figure out if electrons are being added or for the reactants or products, you can add them because they're negative electrons. Zinc doesn't have a charge, This zinc has a positive 2 charge, and you have to have charges balanced. So if you add 2 negative electrons to this side, positive 2 and negative 2 goes to 0, and that's the same charge you have right here. So this zinc has lost electrons. This zinc is being oxidized. Oxidized and reduced always relate to the reactant. Now, something that's oxidized is then also called the reducing agent. So if you look at this list here, all right, zinc oxidized could be, here's zinc oxidized, but zinc is not reduced, so it's not going to be B or D on this particular problem. Now, vanadium is weird. You can use the oxidation numbers. You can figure out that this is a positive 5 vanadium, and this is a positive 4. So this vanadium is actually gaining an electron. It's being reduced, all right? But by default, if this is being oxidized, this one has to be reduced. This is yin-yang. You can't have one without the other. So by default, this guy is going to be reduced if you see the electron cool. If you don't, it really doesn't matter. That also means that this is an oxidizing agent. So what you want here is zinc that's being oxidized, and then this vanadium thing is the oxidizing agent / reduced. So the terminology is weird, but again, remember, if you see one of them, then the other one's going to be the opposite. Oxidation numbers can help, but honestly, just yin to yang. One's oxidized, the other one's reduced. Good to go. Question? All right. I will totally talk about rice milk with you. If you come down, we'll talk about that. But otherwise, if you have any assignments to turn in, I'll totally take them. Have a great day. See you on Friday.